Let's now look at definitions of energy and how that relates to other variables at the microscopic scale. Previously, we've talked about macroscopic kinetic energy. If you imagine, for instance, picking up your canister of gas and throwing it across the room. We've also thought about thermal energy. Now we're going to think about molecular kinetic energy. Note that we're using this thing that looks like a funny distorted E. That's the Greek letter lowercase epsilon. And we're going to be using this different letter to represent that that is the energy of a molecule, right? So E is for the system, capital E, and so we're going to use lowercase epsilon, so funny looking E, for a molecule, just so we can distinguish it. We will have equations that actually have both. So if we just think about the kinetic energy of one single molecule, the equation works the exact same way that we saw many chapters ago, that it would be 1/2 mv squared, where m is now going to be the mass of your molecule, not the whole system. So if we then want to say what the average energy of our molecules are, if we assume that the mass is all the same, and right now all of the work we're doing, we are assuming all of the molecules in our gas are the same, so m is constant, but v is different. Remember that the speeds are going to be a distribution. So within one volume of gas, we would say that each molecule has a slightly different speed, so they cover a whole range. So that means that their energies are going to be a distribution as well. But we can talk about their average kinetic energy, which relates to their average speed, and in this case that would be the RMS, the root mean square speed, since that's what we typically use. So what's the point of this, other than just defining a new symbol? Well, we've already related pressure to the root mean square velocity. That was in the previous video. So now, can we actually relate temperature to kinetic energy? And something that we've said in the past chapters was that temperature, thermal energy, has something to do with molecular motion, but we haven't been able to define what up till now. So we can use our previous result and some other things we know to actually now take this and go to kinetic energy and temperature. Before, we derived the result that pressure relates to the number of molecules divided by the volume, mass of the individual molecules, and then that root mean square velocity with a factor up front. So this is what we already found. So now let's relate this to kinetic energy, what we just defined. Now this isn't too hard, we just have to reorganize a little bit. And what I want to have is 1/2 mv squared, where again that's VRMS. Now note that this 1/2 I pulled into the parentheses, but I didn't originally have a 1/2. So note that the top becomes 2. This way 2 would cancel with 2, leaving 1/3 what I originally had. So this is kind of a nice mathematical technique. You can make fractions appear as long as you have factors out front that cancel. So now you can clearly see that my average kinetic energy was just that term, and that's going to be per molecule. So this is helpful, except that this relates it to pressure, and what we would like to do is have a relationship between temperature and kinetic energy. So we need to go back to another piece of information, which is simply the ideal gas law. This is helpful because the ideal gas law includes temperature. K is just a constant, so that doesn't matter. We already had in our equation up here P, V, and N. So what we want to do is now relate temperature to what we had up here. Now I'm going to skip a step, but note that here I had P and I have V over here. So effectively what you could do is imagine taking this V and moving it up here. And so then P times V would be 2/3 N times this kinetic energy. So we have that. So now if I look at just this part of it, we see that we can cancel N. And then we're left with KBT equals 2/3 E average. So rearranging and solving for E average, I get 3/2, just invert the fraction, KBT. So this is really beautiful. Let's stop and actually appreciate what we found. We found that the average kinetic energy per molecule, and we've been deriving this for actually a monatomic molecular gas, so really just single atoms, is 3/2 kBt. This means that our temperature and our kinetic energy is directly proportional. and 3/2 in kb is obviously just a constant. This means that if we have the temperature of our gas, we know the kinetic energy of our molecules. Now note that this doesn't depend on mass. This doesn't depend on the type of gas other than what we've said is that this is monatomic. So obviously over here depends on mass, but if the only thing we want to talk about is the kinetic energy, we don't even have to think about the mass of the molecules. We just think about temperature. So this is a really helpful result. We now have a relationship between the temperature that the gas is at and the individual kinetic energy of the molecules. So our macroscopic view is that we had a container of ideal gas and we've defined certain state variables. The number density, the pressure, the temperature, and so on, the volume. Now, microscopically, we do still care about the number density, but now we've been able to actually talk about their average kinetic energy relating to the VRMS and the mass per se. Now, temperature is actually then a measure of our average translational kinetic energy. That's what we're saying right now because we're just thinking about monatomic gases. We'll generalize this a little bit in a second. Now, note that before we really just waved our hands about what temperature meant in the macroscopic model for the previous chapters. So this is a rephrase of the previous equation. Again, you can either say E average is 3/2 kBt or T is 2/3 over K, E average. Now, then you can go back to your definition of how the energy, the average energy per molecule relates to mass and VRMS, and you can get a relationship between the average in an RMS, root mean square definition, the average speed, how that relates to temperature, and then that does actually relate to mass. So these equations are going to be really important for all of our microscopic work with gases. And again, the significance here is that we've actually been able to define temperature on a microscopic scale. So frequently I'll talk about hotter atoms and colder atoms, and all that literally means is that our hotter atoms have a higher higher energy. And again, if we're talking about individual atoms, we don't mean average at that case per se. So hotter atoms have a higher kinetic energy, colder atoms have a smaller kinetic energy. So that's one way to really interpret what hotter and colder means.